Or now we want to learn about discharging method. So we were talking about the proof of Poincaré theorem, and it was computer assistant proof, and we will not prove it, but I want to give you some idea on how it's actually proved. So let's recall how we prove Poincaré theorem. So this structure is two. So one, we show that if G has a vertex of degree 5, a vertex E, then we can extend bicoloring of G minus B to G. So that's what we showed. And then we show that every planar graph has a vertex of degree 5. So these two steps, we prove the bicoloring theorem. Right. So in other words, we first show that if G has a specific structure, then that allows us to extend the coloring of smaller graph to the entire graph. That's one. And we show that such a structure exists. And again, the proof of Poincaré theorem is generalization of these two steps. You show that there are, instead of just one, there are many structures. And if G contains each of these structures, then we can extend our coloring. We show that. And then we show that one of those structures must exist. And what's then discharging method? This discharging method is the method to show two. To show this, we may use this discharging method. So let's define some terminology. A configuration. This is just another name for this substructure. This is in a graph is any structure in G. It could be some subgraph, it could be vertex, it could be edge, it could be base. And base is only when this is plane graph. And we say that this configuration is reducible for a graph property 2 if it cannot occur in a minimal graph not having property Q. So here, what is the property Q? Property Q here is that the planar graph, which is bicolor. So this is the bicolorability is the property Q. And then vertex of degree 5 cannot occur there. If so, and this is a smaller graph, so this is bicolorable, and which extends to the bicoloring of the entire thing. So, which is a contradiction. So this shows that the vertex of degree 5 is reducible configuration regarding this property of bicolorability. The Pera-Haken, together with Cole, they use computer to find the 1936 reducible configuration. And yeah, they show that in each of these reducible configuration, you can extend the full coloring of a smaller graph, subgraph, to the entire graph if such configuration appears on your planar graph. And then show that one of them must exist in the planar graph. Your supposed counterexample of the full color theorem must contain one of them. And this was like long, so the proof consists of a 140-page paper and 400 pages of microfilm, and totally become a book of 741 pages. However, later, I mean, their proof was announced, but it was quite difficult to actually check it. The referee had to check the proof to say that this is correct. And it was difficult because it's too long. Paper is quite long. And people, so here, this was 1976. In 1980, some rumor had spread that there is a mistake in the proof. There is flaw in the proof. And then one guy, Schmidt, actually pointed out specific mistake in the proof. So later in 1989, Apere Haken again published the book that explains and corrected the proof, the mistake that Schmidt pointed out, and then other errors, other mistakes that other people have pointed out. But I'm not sure how much people, accepted this proof. Some people, still have some doubt in the proof, and mostly, people agree that it is proof, but I'm not sure how unanimous the opinion was. So, to settle those, in 1996, Robertson, Sanders, Seymour, Thomas prove it again with the simplified proof. So they reduced the number of reducible configuration to 633. And 32 discharging rule. So I didn't really explain what discharging is, so it's not clear at the moment, but I will explain what this means later. And show that the full color theorem is true. Okay. This proof still uses computer. But the program to check is not so absurd in the sense that nowadays, if you use your personal computer, you can run the program which checks the validity of this proof, within an hour. When I last time heard was like 10 years ago, it runs more than 10 years ago. It runs within 2 hours by your personal computer. But now the computer has also, evolved, so it's much faster, so it could learn much faster. So, I mean, it is widely accepted by the public that this is indeed true. Okay, and four-cardinal theorem is proved, but what's the further thing to do? There is this conjecture by Hadwiger, which is stronger than this four-cardinal theorem. If a graph has no k sub t plus 1 minor, then it must be t colorable. So this is a conjecture which is still open. So planar graph, we know that it has no k5 minor. So with t being 4, this implies that no k5 minor is 4 colorable. So this is stronger than 4 color theorem. And this is still open. This is known for t and most 5. And you might say that, okay, t is known for t equal 4. That means what? K5 minor implies 4 colorability. So that's stronger than 4 color theorem. So you might say that, okay, then proof of this give us the alternative proof of 4 color theorem. But actually, they use 4 color theorem to prove this for t equal 5 and t equal 4. Yeah, also 6, sorry. This is proved for t and more 6. So t equal 5, t equal 6 case, it's proved again, but they use 4 color theorem to prove it. And let's see what is this discharging method. So let's say you want to prove such a statement in every, say, planar graph. Again, what is discharging method? It's a method to prove this second goal. For certain reducible configuration, we want to show that such a reducible configuration, or one of them, they exist in planar graph. So let's say if you have a planar graph with minimum degree 5, then we want to show that there exists some vertex of degree 5 that has at least 2 neighbors with degree and most 6. Let's say you want to prove this statement. Okay, how do we prove this? So we want to prove that if this is not true, if there is a graph which has minimum degree 5, and then every vertex of degree 5 has fewer than 2 neighbors with degree and most 6, then we want to say that the graph become too dense to be planar. That's how we want to prove it. And one of the things we know is that the graph G is 5 degenerate. And how did we prove this 5 degeneracy? We use Euler's formula to deduce that the number of edges is M-3 and minus 6. So this Euler's formula kind of guarantees that your planar graph cannot be too dense. So we want to use Euler's formula. So first, assume that that there is this G is the planar graph where with minimum degree 5 having no vertex of degree 5 with that has at least 2 neighbors of degree M-6. And we further assume that this is a triangulation by adding edges. Because if your original graph satisfies this condition, you add an edge, then it still satisfies this condition. So this later condition is still satisfied because we are making triangulation. Planar graph is still planar graph. And then we know that planar graph has minimum degree 5. So it cannot be higher. So after adding edges, this is still true as long as it is a triangulation. So we assume that. Now what? We define the function on the vertices and bases. So this is plane graph. So this is plane graph. So let's say you have embedding so that you know the bases are there. So what? This function, we say that this is the charge. We give charge. Charge is the value of the function. And for each vertex, you assign 6 minus its degree to each vertex B, and 6 minus the length of twice of the length of face. So each face F. Then what do we know? So this is charge phi, and summation of all phi of say x is either vertex or base. Then what do we get? This is the 6 minus degree of B over all vertex B plus 6 minus 2 times L of F over all bases. Then what do you get? It's 6 becomes 6 times that minus summation of degree. We know that from Hel's-Shake lemma, that's the 2 times the number of edges. Let's say M is the number of edges in C. And this is the 6 times, let's say, number of bases is, okay. Let's write this way, number of bases, and then this, again, the Hel's-Shake lemma over the dual, that the summation of length of the bases is twice times the number of edges. So this is 4 times M. This is what? 6 times N minus M plus the number of base, which is 12 from the Euler's formula. This is triangulation, so it is connected planar graph. So you have. So now we distribute this charge to vertices and base. Now what we do? We discharge this charge to vertices. This charge. So we move this value according to this rule. So what's rule? The rule is that each vertex of degree 5, it gives a charge 1/4 to its neighbor of this vertex, which has degree at least 7. So that's your rule. You apply this to all the vertex. Then, what? Now, there was a number written on each vertex and face. After this rule, now new number is written there. The number has changed. Let's say pi star is the final charge after discharging. Then what? Now we want to claim that every vertex of G has non-positive final charge. Every vertex of G has non-positive final charge. Okay. If you have a vertex of degree 6, then its charge is 0 because you didn't do anything. It is 6 minus what? It is 0. You don't give anything, you don't take anything. According to this rule, vertex of degree 5 gives charge, and the vertex of degree 7 receives charge, and vertex of degree 6, nothing. If the vertex has degree more than 8, then what? And its final charge is what? Initial charge is d minus 6 minus degree, and then from each neighbor, you get at most 1/4. So it's at most this. And then this at least 8. Give me a moment. Right, yeah. So this is what? 6 minus 3/4 degree, which is non-positive. Okay. So now we have two cases. If degree is 5 and degree is 7. If a vertex has degree 5, then what? It has less than 2 neighbors of degree and more 6. So it has at least 4 neighbors of degree at least 7. So it has to keep at least, at least 4, it gives to at least 4 neighbors. It gives charge quarter to at least 4 neighbors. So 4 times 1/4, at least 1 to its neighbor. So it's what? Final charge is initial charge minus 1 at most. And initial charge was what? 1. So it's 6 minus degree, so it's non-positive. So if a vertex of degree 7, in order for this, what? You have a vertex of degree exactly 7. And if it has less than 4 neighbors of degree 5, then what? Then its final charge is the initial charge and most initial charge plus at most 4 times 1/4, which is 0. So in this case, this is non-positive. But what if it has more than 5 neighbors of degree 5? In that case, out of this 7 on this plane graph, you know that it is triangulation, so they are all adjacent. And out of them, 5, there are 5 vertices of degree 5. As C is a triangulation, the vertices adjacent to P forms a cycle, and as it has degree 7, a cycle must have 3 consecutive vertices of degree 5. Then what? And this is what we are looking for. It shows that, let's say that's a contradiction because that's what we forbid. We found the vertex of degree 5 whose two neighbors have degree 5, which was what? We forbid. Then what? This shows that this claim is true. Every vertex of G had non-positive final charge. This is at most 0 for all vertex. And also, for every basis, this is at most 0. Because what? The base, you didn't do anything, so this is at most 2 minus f minus 2L0, which is at most 3, because every base is a triangle. Then what? Then finally, is to the summation of phi star B plus the final charge is non-positive. However, what should be? We just move around the charge, right? So this has to be equal with the initial charge. But what was the initial charge? 12. So 12 is smaller than 0, which is a contradiction. That means that contradiction is coming from the assumption here that there are no vertex of degree 5 that has at least 2 neighbors of degree 6. So that's used twice here and here. So this shows that such a configuration must appear in your planograph G. That's an example of this discharging method. Now you see why it has the name of discharging method. It shows that the certain reducible configuration must appear in planograph. You assume none of them appear, and then use this discharging method to show a contradiction. Okay, let's do one more example. And another direction of research on the planograph coloring is that you consider planograph without certain substructure, and then try to let's determine its chromatic number. One of the example is Groth's theorem that if you have a planograph which doesn't contain triangle, you can color it with 3 colors instead of 4. So this theorem is not too difficult, but also not too short, so we are not going to prove it. But, okay, let's say we have a J phase is a phase of length J. And with that, so there is another conjecture, well-known conjecture, which is called time-ball conjecture. Says that every planograph that may have triangle but does not have 4 cycles and 5 cycles is 3 colorable. So that was the conjecture, but this was disproved. This is not true. In 2017, by Cohen, Adat, and Heptige and Carl, Lee, Delgado. So they proved it in quite recently. But as a recall result, there is theorem by Borodin prove that every planar graph without 4, 5, 6, 7 cycles is tricolorable. Let's prove even weaker result as an application of this discharging method. If you have a plane graph having no pole cycle and no j faces for any j between 5 and 9. In particular, instead of 4, 5, 6, 7, we take 4, 5, 6, 7, 8, 9. And this is tricolorable. So let's show that. So we again consider a counter example, a minimal counter example. Then this G must have, it's easy to check that this has minimum degree at least 3, and G 2 edge connected, 2 connected. So this is easy. So if this is not true, then you have a lower minimum degree, then you just color everything here by 3 color and then you can extend it. And this is also similar. If you have a one vertex here, one vertex here, and you color it with 3 color and color this with 3 color, and then you permute your color so that this vertex has the same color, and then you merge it. So this is easy. And so this is a plane graph, and it's already embedded. Just there is no 4 cycles of length 4. You know that those 3 faces share an edge. So this doesn't appear. If you have a triangle, the face of length 3 and then another face of length 3, they don't share a edge together. So our reducible configuration is a cycle of length 10, which have degree all 3. Maybe 2 of them could look like this. But anyway, so this is 10 face of length 10, where every vertex here has degree 3. So this is our reducible configuration. And it's easy to check that this is indeed reducible configuration. Why? You color everything else. You delete this space, and then in the remaining graph, it is 3 colorable. And then you color everything else. Now, let's say this is colored by color 1, 1, 2, 2, 1, 3, 2, 1, 3. Then what you do? You have this even cycle. And then what? Now, this has to be either colored with 2 or 3, 2 or 3, 1, 3, 1, 3, 2, 3, 1, 2. You have a list of size 2 on each vertex. And then you know that the even cycle is 2 choosable, 2 least colorable, so that you can complete your coloring. So that's a proof that this is indeed a reducible configuration. Okay, I'm not gonna write it down. And again, we want to use discharging method to prove that this configuration is unavoidable. So again, pi is initial charge. So again, let's use the same, similar charge. But Okay, now I have written with the flipped side. So before it was 6 minus degree and then 6 minus length, but now I moved this 6 to the other side, and then here we write it first, but essentially, I mean, it doesn't really matter. But now I have changed the constant multiplied on the degree and the length of the base. Then what do we know? Again, the Euler's formula, the summation of these charts is what? Summation of 2 degree, which is the 2 times number of edges minus 6 times number of vertices, plus, no, 4 times. So this is 4. And 2 times number of edges minus 6 times the number of bases. Then what? This is 6 times, negative 6 times number of vertices minus number of edges plus number of bases. By Euler's formula, this is negative 2. So, we know that there are no bases. We assume that there are no bases with the length 4 to 9. So, the only object with initial negative charge is are bases of length 3, which has charge negative 3. And everything else, I mean, this is positive, and then this is also positive, minimum degree at least 3. So they are only the ones with the negative charge. Now this charge is, I mean, negative. So to get the contradiction, we want to show that every object at the end has a non-negative charge. But everything else already have a non-negative charge except this one. Now we have rule, our discharging rule. But we have 2 rules. It's 3-phase. It takes 1 from its neighboring phase. So you have a 3-phase, and then here phase, 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 and it gives 1, 1, 1. And we know that this neighboring phase is not a 3-phase because we know that there are no 2 phases sharing a edge. That's first rule. And second rule is each phase F take 1 from its incident vertex B with degree 4, which is lying on at least 1 3-phase sharing on edge with F. What it means is that if you have F so assume this is the case, then what? Then this is the vertex with degree 4, and it is lying in 1 3-phase here that shares an edge with this F. So that means this gives 1. But this does not give 1 because this has degree at least 4. And let's say this is the case, then this also does not give 1 because it has degree at least 4, but let's say here, there is no edge. And this does not give you to here because this is degree 3, but there is no triangle, no 3-face. That contain this. So this does not give. This also does not give. This gives 1. This gives 1. This gives 1 to this F. So that's our discharging rule. And that pi star is the final charge. Absolute discharging. Then what? For each vortex B of degree 3, its final charge is 0. Because initially it was negative 3, and then we take 1, 1, 1 from its base. Okay, so vortex has one other vortex. But for each vortex B of degree say J, which is at least 4, but its initial charge is positive, but it may have to give some charge to the base. Then, but it gives charge for each 3-phase F containing this B. So, when does it give? So, in order for this has to give the charge to here, this base, then what? This phase must be a non-3-phase, and then there must be a 3-phase here that contains it. Then this gives charge to here, and then this same triangle makes this to give charge to another one here. And again, there is triangle here, then it may have to give the charge to this base and this base. You see, out of these bases, this has degree J, so there are J bases. Out of them, the ones taking charge, there are either 1 or 2 that takes charge. There must be another triangle here in order for them to be able to take the charge from this point. So each 3-phase F containing V shares on H with at most 2 phases containing V. V loses charge. The most efficiently losing case is this picture. So there is triangle and then non-triangle, 3-phase, and non-3-phase and 3-phase, non-3-phase. The non-3-phase, 3-phase, non-3-phase. So, you have 1 triangle and then 2 non-3-phase, and then 1 3-phase, 2 non-3-phase, 1 3-phase, 2 non-3-phase. That's the most effective case. So you lose charge at most 2J out of 3 with the floor. Then this shows that initially this was 2J, but now you subtract that much, and this is at least 0. Okay, so this shows that every vortex has a non-negative final charge. And what about phase? for a J phase F with say at least 10, yeah, so here I said vertex and then explained about phase. So let's add for each 3 phase F, its final charge is 0 because, it takes 1 from 3 sides. And for each vertex of degree 3, its charge is also 0. It doesn't change. So only remaining thing are the bases with length at least 10. Okay. Then how much it lose? You have this picture. So what? Let's say this is degree 3 and this is degree 3. Then it loses 1. It loses 1. It loses 1 to this triangle. And it regains 1. Regains 1. So in total, it loses 1 on here. If this has degree 3, if this has degree 3. If this has degree 4, then you regain, so you don't lose anything. So what does this show? It shows that it loses charge 1 for every path along its boundary, such that so this is the path. The neighboring bases are triangle, and the point have degree 3. And if F is 1 to each of those bases, but regain 1 from its internal vertex. Of the path. So it gives 1. It's an endpoint of a maximal such path. As degree 4 or at least 4, then there is no net loss. So then what does it say? As the net loss is at most half of J with floor. Why? You have this, and then the worst case, the most losing case is that is this case. There is triangle, and this path has length 1, has length 1, length 1, length 1, length 1. They cannot overlap. So its final charge is subtracting that gives us that J minus J floor minus 6, which is non-negative if J at least 11. So if F is 10 cycles, then what? Then its final charge is again non-negative unless it loses 5. And then that requires 5 such passes. And then there are exactly 10 vertices. So this has to happen. But this is exactly one of the reducible configurations that we have forbidden, right? We assume that we show that this is reducible configuration, that every vertex here at degree 3. We don't care whether they have the same, they are to the same vertex. The end point of this edge, the other end point are the same or not. This is reducible configuration. But I mean, that's the only way that this has negative charge. That means that it is non-negative charge. As the summation of all final charge must be non-negative. But again, this is contradiction because our initial charge, due to the Euler formula, is what? Negative 12. A contradiction. So that means one of the reducible configuration must appear. And that if you you can extend the coloring of a smaller graph into the larger graph. So that's an example of discharging method. And then this was only when there were two rules and one configuration, one reducible configuration. Okay, technically you have one reducible configuration, two reducible, three. So this means that the vertex of degree at most 2 is reducible configuration. And this means a cup vertex is a reducible configuration. And this is reducible configuration. So you can say that there were 3 reducible configurations, and then there were 2 discharging rules. But the Pohl-Carroll theorem, as I mentioned, it has much more reducible configuration and much more discharging rule. So it's quite complicated. I mean, I didn't try to read this, but I can only imagine how complicated it is. And for other theorem, for example, this theorem, I also didn't really read this paper, but this also had like more than 10 discharging rule, and then several, tens of reducible configuration, and that was quite complicated. Anyway, so we have learned about what discharging method is, and then I hope you got some flavor of it. And next time we will talk about some other subject of Ramsey theory, which is also very fun topic. Yeah, that's how we'll talk about next time. Thank you for listening. I will see you next time.